Okay, so at the end of class last time we started to talk about vector fields, and I promised I'd proceed into line integrals. But let me go back and talk about vector fields a little bit in a little bit more depth, and then I'll move on into line integrals probably in another video. So first thing I want you to recall is what a vector field is. We sort of were thinking about it in the abstract as a force field. So at every point, you could calculate the forces being operated on an object at that point, and you could calculate that as a vector, or picture that as a vector anyway. So let me give you a formal definition of a vector field. So I'm going to do the definition for the two-dimensional vector field, but you'll be able to extend that naturally into 3 dimensions. So given some subset of the plane, R2, so some subset D of the plane in R2, a vector field is a function f that assigns to each assigns a two-dimensional vector calculated by the function to each point x, y, and d. In other words, for every point in D, I'm going to give you a vector. So you give me a point, I give you a vector. That's what my function does. So let's do a quick example, and this is easy to see. So let's let f of xy be the vector field defined by, well, you give me the point xy, and the vector is going to be minus y comma x. Or if you prefer the ij notation, you can use minus yi plus xj. So this is a vector field, and we can let it be defined on all of R2. And let's calculate a few values for f for our vector field. So f of 0, 0 is 0, 0, right? What does f really do, capital F? It switches the order of your inputs, puts a negative in front of the first one. So f of 1, 0 is 0, 1. F of 0, 1 is minus 1, 0. F of minus 1, 0 is 0, minus 1. And f of 0 minus 1 is 1, 0. Now, of course, I think you can easily plug these things in, but just calculating a few points like this won't give you any sense of how the vector field operates. So, for instance, if you were going to think about the gravitational field around Earth, and you put Earth at the origin, and you wanted to let the vector field represent the gravitational attraction on any object around Earth, then you would expect, if you had an object, say, in the position 100 miles above the Earth, that the vector would point straight down towards the center of the Earth. So all the vectors would be pointing in. But this sort of a few individual values doesn't give you that sense. So there's a way to picture vector fields. And one way to picture a vector field is to pick a bunch of points in your set, in this case in the xy plane, and then draw the vector that f gives you at each point where you calculate f. So let's use that function from above. So this is the vector field minus y x. Oops, sorry, that should be an angled bracket. So at each point I'm going to draw the vector. So for example, f of 1, 0 is the vector 0 minus 1. Sorry, it's 0, 1. So that's the vector 0, 1, which is the vector pointing 1 in the y direction and going neither left nor right, so 0 in the x direction. And this would be the vector, and I place that at the point 1, 0. So I put the vector 0, 1 at the point 1, 0. Here I'm going to put the vector, let's see, that's f of 0, 1. Oops, I'm using a capital F for that. f of 0, 1 is equal to minus 1, 0. So I'm going to put the vector minus 1, 0 at the point 0, 1. That's this vector here. So if I continue doing that, and let me get rid of this stuff so I can see my vector field, and I'm going to use the same blue color here if I can find it. If I continue doing that, then for example at the point 2, 2 you'll have the vector minus 2, 2, so it'll be going minus 2 in the x direction, 2 in the y direction, so it'll be going like this. And if you put in the vector 3, 0, you'll get 0, 3. And what you'll find, if you do this, is you get these vectors that are kind of increasingly long and kind of circling around the origin. Notice if I kind of followed the flow of these vectors, if I were a particle in this vector field, I would be kind of flowing around here. And as I got in close to the origin, the vectors are smaller, so I would be flowing slower. As I got outside here, if this were force, vectors of force, and there were a particle along this pink line, it would be pushed in a circle increasingly quickly if I were further out from the origin. So way out here, I would be pushed in a circle very fast. In close to the origin, I would be pushed by small vectors around a small circle. So where do vector fields come from? Well, they certainly come from physical situations, but mathematically, one vector field we've already done is the gradient vector field. So remember, given a function of two variables, f of x, y, the gradient of f is the partial with respect to x. It's the vector created by the partial with respect to x, partial with respect to y. And in particular, the gradient at each point, evaluated at any given point, gives you a vector. Right? So if I evaluate the gradient at AB, then it's the partial with respect to x evaluated at AB and the partial with respect to y evaluated at AB. So in particular, that's a vector. So the gradient of f gives you a vector for every point where the function f is defined, or at least where the gradient is defined. I guess I should be careful there. So we already have an operation for finding one kind of vector field. It turns out to be a particularly important kind of vector field. So a little notation, or a little vocabulary, and a question. One thing you might ask yourself is every vector field the gradient of some function? It turns out that it's not. So definitions: a vector field f is called conservative, and we'll give some sense of what conservative means when we do line integrals, if that vector field is the gradient of some function. And in this case, that function here is called the potential function of the vector field. And there's an example in the book with the gravitational vector field that you should read. That's on page 728 and 729. So just really quickly, the vector field given by 2xy and x squared minus 3y squared is a conservative vector field, or is conservative, since it is the gradient of this function. Now you may want to check that. Well, what is the partial with respect to x of this function? Well, remember, I treat y as a constant, take the derivative with respect to x, so I get 2xy, and then minus y cubed. But y is being treated as a constant for the partial with respect to x, so I get 2xy, and then the partial with respect to y is, well, x is treated as a constant, so this becomes x squared minus 3y squared. Aha! So this is conservative. So I'll give you a sense of what conservative means when I do line integrals, possibly in another video.